Okay,
Yes.
thank you. Thank you very much. I always like to start my talks at ICTP for the new group with a very small anecdote that many years ago I was just invited to one of these meetings by one of the physicists, and they asked me to sit next to Salam, the great Salam. And I was very excited about tropical predictability those days and climate predictability, and I was giving him all this big spiel about how developing countries in tropics, climate is more predictable, and I didn't think he was paying attention to me, so because he's a great man and he has, but then suddenly he stopped in the middle and asked his deputy director that, you know, I think this guy, we should start some activity in weather and climate. It's very interesting. And I was so excited. I said, oh, great, Dr. Salam, this is wonderful. We'll start. And then by the time dessert comes, he looks, turns to me and he says, and you are in charge. Can you start from? So that's kind of feudal lord he was. You know, he could just make a decision. But then, of course, thanks to Filippo and Fred and other Molteni, I mean, we really have here a great group now. And it's always such a pleasure. I was not planning to come to this meeting, and I had to meet. Oh, by the way, that's another anecdote I'll tell you. If you want to meet Filippo, the best time is come here when there is activity he's director of, because then he's here. Okay. So my talk was basically planned at the very last moment. So when I came and I saw the contents, I thought there is something that I have to say which may be relevant to this meeting. You actually have been using these words. So by the way, it will be a very informal talk. I have actually slides for an hour, but I'll just take a few minutes. I'll skip over a lot of them. You have been hearing the word uncertainty a lot. Of course, that's the topic of this, and also sensitivity. Okay. Well, I'll introduce three new words to you. One is predictability. Another is the model fidelity, which is kind of same as accuracy, and another is the seamless prediction, or the seamless predictability. Now, one of the things that we have not touched on in many of the discussions when we talk about uncertainty in the simulation of the mean climate, the actual mean climate. I mean, I don't mean 100-year mean. I really means take last 100 years of mean, variances, covariances, structures, the whole thing, the entire observed spectrum of climate for 100 years. So the uncertainty in that, or we're talking about uncertainty in the response of the external forcing. Are we talking about the uncertainty in, and of course they are related. And why I want to distinguish that, because it gives you a nice framework to understand what problem we face. In our very introductory lectures in dynamic meteorology, we always learn that the mean state determines the instabilities. After all, when you look at a weather map and you see a disturbance, that's what our dynamic meteorology has taught us. These are instabilities. They can be barotropic instability, baroclinic instability, convective instability. But it is not a big news that mean state determines fluctuations. So therefore, it's a very simple extension that if you have error in the mean state, there will be error in the fluctuations. So therefore, we have to think of the errors in the mean state versus errors in the fluctuation. And Filippo asked the question about bias correction. I will come to that later. But from seasonal prediction time scale, we have done a lot of study, and it turned out there's no shortcut. If you put a bias correction in your model, you remove the bias completely. Your prediction changes zero scale. So in other words, there's no shortcut. So ultimately, you get improvement in the skill only when you make a fundamental changes in the physics of the model and the dynamics of the model. So that's, and I'll actually show an example. So I think I just wanted to give you a sort of the conceptual framework to ask some more questions than we have been asking. And when we are talking about uncertainty, I'll try to define sort of three kinds of uncertainty. Just think about this. One is irreducible uncertainty, that you cannot reduce. You can have perfect observations, perfect models, everything is perfect, still you cannot reduce it. See, that brings you the concept of predictability. because that's why I said that we have to pay attention to the concept of predictability, because there is an irreducible uncertainty, but then there is uncertainty due to the poor knowledge, and that's what we have been discussing a lot, structural, parameterizations, resolution, physics, and so on. But we really need to at least pay some extra attention to the what kind of uncertainty is simply because our model's climate is so bad, so wrong, so incorrect. Why I'm saying that? Because I have basically been trying at the World Climate Research Program when I was in JSC, try to make IPCC a major element is to model errors, just a description of how good the models are. But as you can see from the previous talk, it's not easy. It's a very complex question, but of course, IPCC, you know, I doesn't stand for international, it stands for intergovernmental, which means every government that submits a model is good. Now but this question is very difficult to decide, so you have to give your opinion, so I'll share with you my opinion. My personal opinion is that model democracy is not good. I love democracy, but I don't think model democracy is good. I really think that there are models which have terrible simulation of the mean state. But they are there in the ensemble spread, and we're spending all our time looking at the spread and so on. But I know where do we go for it. So that's one of the questions. And by the way, and the second thing that we have a problem is that we assume that there's no correlation between the model bias and the response. I don't think that's not correct either. In other words, no matter how bad is the mean state of the model, we assume that, oh, you've doubled the CO2 or put sea surface temperature and you subtract 2 minus 1, all the errors will subtract out. Not good idea. That's really the essence of this, because it's not a linear response. So simply because, as I told you, the mean state determines the fluctuations. So you have changes in the mean state. So I think that these are two concepts I wanted to keep in mind. The third one, before I go on my slideshow, is the idea of seamless prediction. And that's another concept that World Climate Research Program really pushed it through a program. Why I call it seamless prediction? Okay, so it's very clear from some of the talks that you heard before. Society doesn't feel the effect of delta T, whether it's 2 degrees or 2.5 degrees or 3 degrees. Society doesn't actually care. Society feels the effect of regional manifestations of extreme events. So what will happen? In a changed climate, you will change the mean state. That mean state will change the fluctuations, and it is the statistics of those fluctuations which will be felt by society. And when we talk about adaptation, same thing. We don't adapt to 2 degrees warming. We adapt to new statistics of extreme events. We adapt to, so if your model doesn't have hurricanes, as the example was given about monsoon, well, let's go to hurricanes. Suppose your model doesn't have hurricanes, and you have a new climate change model, how can you trust its fidelity in predicting what will be the change in the hurricanes? So we really need models which can, in the control simulation, have the good statistics of hurricanes. I know we cannot predict hurricanes beyond a few days because we come to the chaotic limit of deterministic prediction, but we must have the statistics right. Same thing with El Nino. Suppose, I mean, we know so well in the last 20 years how strongly regional climate variations depend upon El Nino. You saw the examples, El Nino or La Nina, you can be completely different. But suppose your model doesn't capture El Nino or La Nina, well, how can it capture what will happen in the future? So these are very tough questions, and I really think that we really need to pay attention, and we have to broaden the definition of uncertainty to include seamless predictability and the sort of the relationship between, because weather, season, and climate and decadal and climate change, they are not separable. Okay, there's no wall between weather and climate. Okay, I mean, we do that for our. So I think that I just say my talk having given that background, the actual, some of the results that I'm going to show you are only confined to the seasonal time scale. And there is sort of very much like what you were showing in this. Particularly, I have been very interested in the monsoon predictability. And as you saw, monsoon, the models have a terrible problem in predicting. I'm also interested in the ENSO predictability. And ENSO is a very good example. In the morning, you heard about very inaccurate but very precise result. Okay. Right? You heard about, right? That was very, very nice. So I'll show you examples. That's what's happening with the models now. They are so wrong in simulating the actual temperature, but they're so reproducible that they all give certain wrong amplitude of El Nino. Good thing is that we're still able to get some signal out of it. So it's really a good news. I don't want to discourage you, and I don't want you to get discouraged by some of the results that he showed you in the last 20 minutes, because we are just learning. You know, you are the first generation coupled climate modelers. There was no climate model when we were going to school. There was no coupled climate model. We had AGCMs, and their resolution was 5 degrees by 7 degrees. And we used to get so excited about it. Look at that, what we have done with it. So I think we have to learn a lot in this. So that's just my general introduction. Now let me see if I can and you have to give me like 5 minutes or so notice so that I can at least conclude some of the things, because, okay. So
if you want me to tell you, how much time do you want?
You just give me a
What time do you want to stop?
Oh, no, I'll never stop. I'm saying unless he tells me. I'm sorry. I'm just saying unless he tells me to stop. So that's why I'm telling him to tell me to stop.
Okay. I'll tell you when it's 20 minutes from now.
Oh, okay. Okay. All right.
According to Mr. here.
Okay. So that means I just said I want to have 5 minutes for discussion. So the questions. Okay. All right. So I just say so I have introduced you the topics that I told you, okay, seamless predictability. One section, so what to do about it? What are the challenges? I will not go into that because that sort of is national, international, and so on. I will do. But I think that this slide I show simply because everything is there in one slide. You see decadal fluctuations, you see El Ninos, you see, I know, you can actually identify an actual El Nino, you're right. Well, you just have to imagine, you can see the El Nino, right, 97, 98 El Nino. Let's just go. Monsoon, he showed you, look at the rich structure of the mean monsoon. And this is what our target is to be able to simulate. Now, we're trying to predict its change in the mean climate, and we cannot capture this. This is what I'll show you what we do. And now, what is monsoon? Rainfall. It comes out of disturbances that form. Those of you who are familiar with the monsoon, these are instabilities. These are instabilities that form in the Bay of Bengal, they propagate, and once they form, and look at the resolution required. I mean, Himalayas is right there, and these cyclones, you see, were passing through the walls of Himalayas. So if your model cannot capture that, you know that you can be able to do that. Yet, here is the beauty of our climate system. Yet, if you look at the 100-year time series of the monsoon rainfall, you find some year there was a huge drought. Over whole India, there was a huge drought. Same thing with Africa, same thing. So in spite of all the chaotic nature of the weather fluctuations, there are large-scale persistent anomalies, and they are the one who gave us the scientific sort of encouragement that, okay, there may be predictability beyond weather. And by the way, if you look at all the red slides, red bars, those are the years where there was El Nino. So you see a very direct relationship. If there is a warm event in the Pacific, you will have a drought, monsoon drought, because all the negative rainfalls are mostly red. Not all of them, but most of them are. And by the way, that's how India Meteorological Department got created. You see that big drought in 1977 and then 1918, and the British government in India didn't know what to do. So they brought Walker, the famous Walker, they brought to India as head of the Indian Weather Service, And he started correlating India's rainfall with everything in the world. That's how he discovered Walker circulation. So weather prediction is our success story, all right? So I would like to address all three: weather, seasonal, and climate change. So let me just give you, weather is our success story, right? For 40 years, constantly increasing the skill. Why? What is the reason? You can argue better data, better model. Well, let me just tell you one example that you will realize that it is because of better model. So what European Center did is that, okay, you see the rainfall, I mean the skill is increasing, took the model of today and go back 30 years and then do reforecasting. Now you don't see any difference so in the lower curve. You see the skill is almost flat. So look at that means that so this is a point which I'll come again and again, because the lesson I have by the end of the lecture is that our biggest challenge is to improve model fidelity. If we improve our model fidelity, it will improve our weather prediction, it will improve our ENSO prediction, and it will improve our confidence in regional prediction of climate change. That's sort of a kind of underground agenda that I'm trying to drive, okay, towards in this talk. And I have no way to prove this, but this is we have published papers on this, that if a model has high fidelity, it will have high predictability. This question came this morning, a couple of times, also yesterday. How do we know which one is a better model, and how do we actually determine this? But you know, the common sense sounds reasonable, isn't it? Suppose a model is very good in simulating hurricanes and El Niños and monsoons and the 100-year fluctuations in last 100 years. I will feel that that model will be a little bit more reliable for future. But I have no way to prove it, but I'm just telling you, that's why I call it a hypothesis. But I cannot prove it for climate change, but I can prove it for weather, and I can prove it for seasonal. And weather is well proven already, and now I'm going to show you for seasonal. By the way, a question was explained this morning, what is relative entropy? How do you measure model fidelity? How do you know which model is good? You know, our normal metrics of root mean square error, not good, obviously, because you can have a big error in one place, and when you take the square, it just dominates. A few bad points can dominate. You can have alarming correlation. That's not good either, because you can have a very large error in the amplitude, but pattern may be good. So that's why I think the information theory people, which basically started with the economists, have come up with this metric called relative entropy, which basically measures the distance between two PDFs. And several papers have been published in our field. Tim Del Sol and many other people in my group have done. We did that for the seasonal prediction and also for climate change. I'll show you two examples of this. So this is the last IPCC. So we took, so what we did is that we took the 100 years of observed global sea surface temperature and 100 years of simulated sea surface temperature by IPCC models, okay, and calculated the relative entropy between them. You can say calculated the error between them, but error is now this relative entropy, which is a distance between the two PDFs. And then looked at each one of them, that is the model's ability, how good it was in the 20th century, had any impact on what was its sensitivity of double CO2. And sure enough, it's not very strong. We had only 14 models. This was published. And we found that, by the way, relative entropy is the measure of the error. So if it is 0, it's a perfect model. Think of it that. So any model which has very low relative entropy, the x-axis, that means a good model, if you want to call it. If the relative entropy is very high, that means the model error is very large. And the sensitivity is now, we are hoping to repeat this again for CMAP5, but at least there was a suggestion that if a model is good in simulating the 20th century, that model is predicting higher sensitivity. So in a way, it was left as a question which some people agree, some people don't agree. As a matter of fact, I was one of the co-authors of the chapter in IPCC, but some of the members of the chapter will not allow this figure to be shown in the chapter because they thought it's too controversial, because we cannot prove that it is the case. But we can do it for seasonal prediction. So we have 7 models at European Center. There was a project called Provost, and each one of them have now seasonal forecasts. So now we can calculate their ability to simulate mean climate and find out what is the skill. And now this is, again, you see a relationship that, yes, the models which have less error in simulating the mean climate have a little bit higher skill. So I'm just giving you examples of why I'm going to end up by making a suggestion that our goal as a modeling community should be to strive towards really building models with high fidelity. And how do we do it? I'll come to that. Okay. Now, you have seen a lot of errors, and I don't want to turn this into a model bashing session, but you know there are a lot of problems models have, and this is my favorite. This is an old slide, but this is the shortwave radiation, okay, observed. 7 different years of measurements. There cannot be anything more basic than shortwave forcing, right, as a function of latitude for our climate system. And you see how reproducible it is from year to year for 7 years. These are our models. I mean, they're just all over. They're all over. So you can do that. That's the fundamental forcing. I can go on. I'll just click on it. Oh, this one is something that really surprised me. Again, I told you that I'm in the monsoon interested. Many of you are actually interested in the monsoon. This is the bias in CMIP3, in the mean of all the CMIP3 models. These amplitudes, if you look at the millimeter per day, they are almost same as the mean rainfall, many of them, okay? Sometimes 70%, 80%, okay? So the bias is pretty large. CMIP3, fast forward 7 years. CMIP3 and CMIP5, I can't believe the similarity between the two. And I just, when somebody showed this in a lecture, this is not my slide, this is a slide of Annamlai and Walser, and I say, oh, wait a minute, are you guys sure you have done the right calculation? Yeah. So you can make the case that there are some very fundamental problems of physical parameterizations, I'll say, more than anything else, because resolutions have gotten a little bit better. Look how, and the same thing for the winter. So I actually think that the problem is convection. So I'm just diverting a little bit just for your information. We believe, and there have been several papers published on convection. So what we did is that we gave 6 best models of the world, identical SST, and say you run for many, many years and calculate the standard deviation, variance. Look at the fluctuation, and it's a politically correct slide. I'm not telling you which model is what. All I'm telling you is that they all think they are the best. Okay, but I mean, this is GFDL, NCAR, NASA, European Center, I think all the models in the world. But anyway, so I think we just have a problem. I told you that I'll give you an example of the monsoon. I think I will. So weather predictability concept you are already very aware of. So let me just give you a very quick rundown on how do we bring this predictability and uncertainty concept once we go beyond weather. In the weather, it's very easy, by the way. You just look at the doubling time of the error growth, and that Lorentz has sort of done this problem. Now we're just trying to do that. And you see, if you have a different initial conditions and boundary, this doesn't go at all. Can you see? Well, think of it on the left side, IC1, IC2, IC3, and each one has a random perturbation. Okay. Then you have 2 metric. One is the variance among the ensemble members. That's what we call climate noise. Another is the variance among the different boundary conditions that we call signal. And when you take the variance, the ratio of these two, that's what measures your predictability. So it's the ratio of the signal to noise, okay, so once you go beyond weather. And there is a very well-known formula. You can go to any statistics book, and you can look at the F test. How do you test the ratio of the 2 variances? One because of the signal, so forced by the SST, one because of the noise. And that's why I was asking the question yesterday to you that when the models are highly reproducible, that means that the noise is smaller, okay? And when signal to noise is higher, that means it's high predictability. But that doesn't mean better prediction. So therefore, that's where the question comes up, predictability and the potential predictability. So when signal is much higher than noise, then you know that you have potential predictability. And we find that again and again for tropical SST, for Indian Ocean SST, that we have very high potential predictability. Challenge is how to get that high potential predictability into real prediction. And in fact, this is when you took that ratio for the Indian monsoon, every point, every model showed very high predictability, but their predictions were not good at all. And I'll just skip on that. And the reason is very simple. I tell you that we have got El Nino and monsoon are related, but only during the monsoon. So that's not a very predictive value. So if your model can predict that there is going to go an El Nino starting in March, then you have a much better skill of predicting monsoon. And by the way, the great Walker was in India for 20 years. He tried to predict monsoon, and later on somebody came and evaluated all his forecasts. He has zero skill. All his forecast has zero skill. And the reason is very simple. He used to take predictors always here in January, February, March. That's where the things are changing, you know, whether it is going up or down, and that's what he used always. Later on, we proposed that let's use the tendency, and suddenly, actually, that's one of the big predictors now for the Indian monsoon, the tendency of southern oscillation, and the tendency of the El Nino. All right, so I think that let me just now skip to the problem we have. So we believe that if you have a big SST signal, you should be able to predict monsoon. Okay? Well, guess what? 1997, biggest El Nino ever. In fact, after 82 or 19, maybe 1887, this was the biggest El Nino. And everybody, all of us, is great. It's going to be a drought. It's going to be a drought, okay, monsoon. Okay, well, guess what? I don't know whether you can see. So you can see the predictions for 1997 for sea surface temperature. On the right side is the rainfall. Look at the observed rainfall in the top, and look at the predicted rainfall. All the models predicted big drought. That's what we're expecting for future. So it was really a wake-up call. That's what I meant. You know what happened really is that El Nino was still very important for affecting the drought over India, but the Indian Ocean had a huge anomaly, and that was not known, that a large Indian Ocean SST anomaly can neutralize the influence of the El Nino, and it canceled, and India basically ended up having a normal rainfall. So that's another lesson learned, that we cannot just fix on one thing and say we can predict the drought. You have to predict the global boundary forcing of sea surface temperature and soil wetness. Okay. By the way, this was the situation with the Indian Ocean. As you can see, El Nino related anomalies, which are normally, you know, the sort of the dipole that you get, that will give you a drought. And then many linear models were done, very simple models, by putting a third forcing, and then it neutralized the Indian Ocean. So it's not just a crook, we understand, yeah?
20 minutes.
20 minutes?
We're at 20 minutes.
Okay, we're at 20. So how many more minutes I have? 5?
Well, I
5?
said you need 5.
5 minutes?
Yeah.
Okay, great. So let me just, okay, so let me just go back to the, where, so I can show you a lot of, let me tell you where I was going. These are the ENSO predictions. Just see how every prediction just goes south. They're highly predictable because they're all same, you see, but they're all wrong. Because this model has such a huge bias in this, and in fact, if you look at this, this is what happens. So you start with any month, the January, and then you right away you go down on this. Now, what is the beauty of it? So this is the error in 4 months, 5 months. Okay, this is where I started. Look at this. So you have an SST error of 5 degrees to 4 degrees. These are the top models of United States now. We're trying to do that. it's quite likely that it will affect our ability to predict. Don't you think so? And the fact that we are able to still do some skillful prediction, that shows how robust the El Nino signal. So this is just the mean of 30 years of systematic error within 5 months. And yet, on top of it, ENSO fluctuations we are able to capture. So anyway, I think that I have shown you enough of the ENSO. So let me just come back to well, by the way, I had a lot of slides on how increasing the resolution, improving the physics can really improve the simulation, and you have seen that. I'm sure you have seen many slides like that. Very high resolution MJO, you get a much better MJO. I think somebody showed, look at the Indian monsoon. Couple models, terrible, but once you have a 7-kilometer model, you get a much better Indian monsoon on the left side. All right, so I think that blocking, somebody showed yesterday blocking, very clear impact. You know, once you increase the resolution, you get a much blocking. So the question is, what is our goal? Our goal is to create this model which captures, and here is my last, where is the main slide I want to show you guys? Yeah, so what is the challenge? This is our challenge, okay? Just as a summary of everything I have told you in the past 15-20 minutes, all the improvements in weather prediction that we have watched in the last 30 years are all basic understanding of the potential velocity dynamics. That's it. We have a much better handle on understanding the dynamics, the large scale dynamics. And we are able to make a much better prediction of 3 days, 5 days, 7 days of the cyclone. Our models, even with the current resolution of 100 kilometers, are able to capture the basic potential velocity dynamics. We cannot capture convection. We cannot capture tropical organized convection. We cannot capture errors into the sort of, that's why the tropical rainfall. That's our big challenge. And I think that what we really need is to be able to develop a new set of models which actually can capture the entire time scale, okay, from the easterly wave to the depression to the monsoon to the El Nino. But it's not going to be easy, right? It's not going to be easy because we are so busy in running IPCC scenarios. No, we are so busy in making a lot of, and modeling groups are not supported to do long-term research. You have to publish papers. You have to write a proposal. Well, how can you do that? Anyway, we have been saying, so we had a workshop, modeling summit we call it, and we said we need a revolution in climate modeling. And we said, just like the physicists have a CERN and ITER, we should have a climate CERN for climate change. And we don't need 30 people or 50 people, we need 500 people who actually are addressing each component of the model, El Nino to the boundary layer to convection, radiation. Anyway, as soon as we made this proposal, in US, the Republican Party came to the power. And they said, anything climate, zero. Anyway, my point is that we have not succeeded in any big way to convince the global community to be able to put this kind of international effort. Still, the efforts are very distributed in every country and some countries. But those are the challenges we face, and we are hoping that someday we will be able to combine our resources so that we can address the entire spectrum from weather to El Nino to decadal to the climate change. Okay, thank you very much. I'll ask any questions.
Questions? Yes.
So, great series of discussions and inspiration, I think, for all of us. The question, I guess, is this notion of the predictability. And I put it down in my notes here. You had a statement which was sort of the fidelity improves the predictability, but this is improving for climate change. So I guess if we're looking at seasonal timescales, do you think that this is going to then move us forward on the climate change predictability and then therefore produce
right? So
improve
this is
our
a question which there is very difficult to answer, and as you can see, the previous speaker was struggling through this question, and I realize but there have been papers published, and there are some people have proposed that our model's ability, the skill in seasonal prediction should be one of the metrics to be able to make an estimate of the reliability and the accuracy for the future climate. And if you come to think about it, just think sort of conceptually. You were talking about, say, 50 years from now, okay? Well, even 50 years from now, we know one thing, that in any given season, say GJA, you are having, in any given season, what will happen over North America or South America will depend upon what are the SST anomalies in that season. So the local simultaneous climate, seasonal climate, is completely forced by boundary condition. Not completely, but largely. I'll say completely, but largely for the predictable part. I'm just saying the only part that is predictable is the one that is forced by the boundary condition. That is, by the way, just to give you a small advertisement. So that's the main result of COLA. I mean, the COLA is the center that we established. That for any given season, you can actually calculate what is the most predictable part. So even 50 years from now, that if your model cannot capture the influence of the today's El Nino on today's North American climate, there's no reason why that will capture just because the El Nino has changed. Do you see what I'm saying? That relation, that impact, that was what I was trying to say.
The translation to the climate timescale is sort of asking, are we going to get the large-scale changes in ocean circulation?
Exactly.
And sea ice and the longer timescale response components of the system.
Yes.
And we don't really have an analog for the seasonal forecast for those types of things, or do you think we do?
That actually we are trying. So for example, we are trying to see if there is an analog for decadal. Say for example, at least for decadal. And we know we are already now in this big uncertainty that, okay, because the data is limited, so we have only a few decadal signals. So how many of those decadal signals are predictable? And if we can make an estimate, because the same argument will apply. Now, that, by the way, your question reminds me of an important comment I forgot to mention in the beginning. Our field should have evolved in the following way. We understand weather prediction, and then we keep improving. Then we go for MJO prediction, 2 weeks, 3 weeks, and so on. And we have some confidence, then we go to the seasonal prediction. And we have some confidence, then we should go to the decadal prediction. And then we should have got to climate change. You know what we did? We did weather prediction, then we went to climate change. Simply because of the society's interest, of course. And I feel that somehow we have missed this step. And we are coming back now, because that's what we have to do, is come back. Because many of the comments that you saw this morning, and some of the comments you made, see how relevant they are to be able to have the model's ability to capture the seasonal and interannual fluctuations, because that's what society will feel. Yeah.
This is a similar question, but yesterday there was a schematic that was put up on a slide that showed that the different time scale of uncertainties and how they affect prediction, and it showed that at the beginning, when you run a model, the internal variability is a large part of your uncertainty. Over time, that disappears, and your forcing scenario comes to dominate your uncertainty. And that was because the sort of the forcing is sort of the dominant problem in climate change, the long time scale. So I guess my question is then, when you said there's no difference between weather prediction and climate prediction, those to me seem to be different problems.
Okay.
And so how can you bridge that gap? I agree that you should build over time, but
okay,
you get to a different place.
Right. Now, it depends upon the metric. Okay. So let's say if you're looking at global mean temperature, then the uncertainty in the global mean temperature, because of the different initial conditions, will completely be dominated by the forcing after some time. My point is that this comment that, or this result, and this has been popular, it has been published many papers, but when you are talking about a regional impact, a very regional anomaly, I don't think that we have that clear that what is the time scale at which it will just be irrelevant. By the way, it's a normal thing to say, oh, initial conditions are forgotten, after a few days. Some people claim they are never forgotten, actually. The question is that where the evolution goes. So it's really a question, in other words, if your question is simply, will climate change, global mean temperature will be 2 degrees or 4 degrees, it doesn't really matter. So but if your question is that should England build that Thames barrier, we need to, that's one of the big questions I have, that how do you know what will happen to the rainfall fluctuations, to the sea level? And so my only point is that we have to address this problem seamlessly. And I know it will be much harder to do, and that's why there's another question. Maybe if we didn't have 50 models, maybe if we had just a few models, probably we could have much higher resolution and address that reasonably. But yes, I think it's a question of understanding what is happening and answering the question at the scale. But when you come to the regional manifestation of climate change, that's where many of my arguments come into picture.
I have a question.
Yes.
I understand your concern about the low reliability for the future climate change projection.
Low?
Yeah, low, and your concern about the inaccuracy of.
Yeah.
Yeah, but the reality is now many studies have been started or conducted about the impact of climate change, impact many aspects of life. So actually, I heard in Europe now seems tended to people move more and more money in the impact or mitigation or adaptation studies. So as a climate physics scientist or community, what kind of message we should deliver to correct the situation?
Okay. That's a very delicate question you are asking, and I would like to be diplomatic in answering that. So you use the word mitigation and also application. So let me just make it clear. Mitigation is not a problem at all. I really think that mitigation is something that we have to do, because at the end of the day, ultimately we want to reduce the amount of CO2 molecules in the atmosphere, right? So no matter what we do about predictability, all these things about forcing will come into, and we know that it will be a different climate. That's not a problem. The question is about adaptation, and that's where people, sorry? The impacts and adaptation, that's a question. If I have to choose what topic to work on, now I will, as a climate physics scientist, I would like to spend my time trying to improve the fidelity of the model rather than finding out, like the US has a third climate assessment. Okay, so this is, you can do the climate assessment, it should be done. Part of it is being done to make sure that the message goes out. But no, I have a very clear answer to your question. I really think that our biggest challenge is to improve the fidelity of models. And if we don't, we will continue to remain in this. I mean, the previous talk was really the best introduction to my talk. I mean, look at the uncertainties that are, as soon as you come down to the actual applications, Indian monsoon, what is happening. So I as a climate scientist, it is such a mistake to think that the climate modeling problem has been solved. And all we have to do is just run models. I just don't feel that at all. We have to, we have to use regional models to get the very high resolution definition. So there always will be regional models, but that you can use them to reduce. But you have to improve the global model. Because if you don't improve the global model, what will be downscaling will not be very good either. Yesterday there was a question about blocking. You remember there was a place where the blocking was very poor in one of the longitudes, okay? You run a regional model on that, you're not going to improve the blocking, because blocking depends upon the planetary wave structure and the dynamics. So society needs something now. So for whatever global model we have, regional models can give us some answer, and we can take that answer and satisfy the society needs. But we must continue another effort globally to keep improving the fidelity of the models. That was my message.
So maybe this will be the last question.
There's a lady, we don't want to say no to her, right? Okay, all right. Okay. Too last.
My question is about the new archive of subseasonal to seasonal prediction that has been in the ECMWF. So it's for 11 models. Now it has been 6 different models has been published their data after May. So for analyzing this archive for regional decision making, should we see whether these models capture the larger scale indices like ENSO, and then go for whether to use them, or we should have another strategy?
Okay.
Or
so
there will be a multimodal ensemble. What do you think of these kind of using this kind of archives?
Yeah, this is about the subseasonal archive you're talking about?
Yeah.
Where people have done the subseasonal predictions.
Yeah,
and many
course.
models, yes.
Yeah.
So, by the way, so that is actually a very good example of how that's a real progress. So we had weather prediction, and in fact, the sub-seasonal prediction came even later than seasonal prediction. We had a lot of success in predicting El Nino and their response. So sub-seasonal. So we are just beginning to find that there is some skill in the sub-seasonal prediction. I mean, by the way, this is so fascinating. That's why you have to keep, when the El Nino response was calculated 25 years ago for the first time, half of the models didn't get any response at all. They didn't get any response. European Center was one of them. Why? Because the models did not have the right treatment of convection and the boundary layer. 25 years ago, 20 years ago, none of the models had MJO, the sub-seasonal. So it has taken us 15, 20 years that now our models have MJO. And now, that's why I said sub-seasonal, and now we have a project where we can now look at the MJO. And absolutely, it is the fidelity of the models in predicting MJO is going to determine whether we can be able to have any skill. Now, when it comes to the climate change, by the way, I personally feel that the society has 2 time scales. One is weather, but the next one is really the season, what will happen. The intra-seasonal is very important now. I mean, Indian monsoon, the planting of the crops and everything is done. I have never been able to think how the intra-seasonal MJO predictability what will do to in the climate change. I haven't thought about it, but I totally agree with you that this should be analyzed with that point of view.
Not going to really ask about modeling, it's slightly different. But you mentioned how a very strong Niño event did not lead to a big effect in the monsoon because of the Indian Ocean, and so how you have to consider the global ocean forcing.
Exactly.
So in Brazil, very often I see a lot of effort from regional climate centers to come up with indices that will have some predictive value, and that people spend, I think, quite a bit of time on that, looking for indices. And I think maybe it's a question of lack of model fidelity for the tropics. We have a semi-arid region. We have the Amazon, which of late has begun to have droughts. So people are always looking for indices. And indices are, I think, maybe a way to bypass this need for a simulation. Do you see, how do you see indices, like based on the, do you see any hope for that?
That, I tell you, indices, in my opinion, are just a reflection of the fact that our field is so underdeveloped. We are making progress. Indices is a shortcut. Indices, ultimately, it's the structure of the large scale flow which determines. I think it is a convenience. Indices are just a convenience. I mean, Niño 3, let me just tell you, Niño 3 has been beaten to death, right? I mean, that's sort of for everything, for prediction. Now, what we are learning for this year in 2014, that Niño 3 had no real importance in predicting the El Nino. It was the structure of the SST in the Northwest Pacific, and especially in the North Pacific. So my short answer to your question is, because we are going for lunch, is that this is just a symptom that we are very slowly making progress. It is easier to be able to have something that you can communicate. Our goal should be ultimately to capture the structure of the large-scale flow, including SST. And now, I have to end with one very positive comment. I'm an eternal optimist. When people thought nothing is predictable beyond weather, I thought, no, things are predictable. That's how we started the seasonal work. So I'm very optimistic that we will make progress. But we will make progress only if we follow the path where the progress is possible, and that is to start building models with high fidelity.
Let's thank our speakers.
Okay, thank you.